into a realm of computing that promises to be not just faster, but fundamentally different. We're exploring the potential of photonic computing using light, photons, not electrons, to process information.
That's right. And we've gathered quite a stack of your sources, the articles, research papers, notes, and they really paint a picture of a technology moving pretty rapidly.
From theory to practice.
Exactly. And it's being driven, really, by the growing limits of our current electronic world.
And that's the core of it, isn't it? Our electronic computers, these marvels of modern engineering, well, they're hitting physical barriers.
Yeah.
That decades-long ride on Moore's law, the relentless shrinking of transistors, it's kind of running headfirst into fundamental physics.
Absolutely.
Yeah.
And the sources really highlight the big roadblocks.
Yeah.
Generating immense heat, demanding, frankly, unsustainable amounts of power.
Right.
And facing increasingly problematic signal delay, or latency, as components shrink and connections get denser.
So, our mission in this deep dive is to take this stack of material and really understand what this shift to light actually means.
Okay.
What are the fundamental advantages of using photons? How do those translate into, real-world benefits?
Where will it likely make the biggest impact?
Exactly. And what are the hurdles still standing in the way? And maybe why is this happening now?
Right.
Consider this your shortcut, basically, to getting well-informed on a potential revolution in computing.
Okay, so let's start by really digging into that problem electronic computing is facing.
We've seen incredible success, truly mind-boggling progress, just by shrinking transistors following Moore's law. Billions packed onto a single chip.
And that density fueled unprecedented power, no question. But as transistors approach atomic scales, well, they encounter fundamental physical limitations.
Like what?
We're talking quantum effects, starting to mess with predictable electron behavior.
Ah, okay. And when you pack that many microscopic heat sources onto a tiny piece of silicon, well, things get hot, really hot.
Exactly. The heat generation is immense. Cooling systems, particularly in large data centers, they're becoming a significant infrastructure challenge.
And they consume vast amounts of energy themselves, right, just to stop things melting.
Precisely. Which ties directly into the overall power consumption issue our sources emphasize. Powering these increasingly dense, complex electronic systems is becoming incredibly energy-intensive. And then there's the inherent signal delay. Electrons moving through even the best conductors, they encounter resistance, capacitance. It slows down signal propagation.
So even if the transistor switch is fast, getting the signal there takes time.
Right. As chips get larger and denser, the time it takes for signals to travel across the chip or between components becomes a real performance bottleneck, a significant source of latency.
So it's not just about making things faster anymore. It's about managing heat, power, and, well, fundamental signal travel time.
Precisely. Electronic computing is facing a multifaceted wall. And this is where photonic computing steps onto the stage, offering a fundamentally different physical approach.
A way around the wall.
To bypass these specific growing challenges. Yes.
Okay, if that's the problem, let's turn to the solution. What is it about light, about using photons instead of electrons, that offers this kind of potential breakthrough?
Well, what's truly fascinating, as the sources detail, is that the advantages stem directly from the intrinsic physics of light itself.
Okay, let's start with the most obvious one. Speed. Photons travel at the speed of light. Electrons, significantly slower, especially inside a conductor.
That's the foundational difference. And this isn't just a marginal speed bump. It translates to orders of magnitude faster data transmission potential within a system.
Right.
And the inherent capability for much faster computational operations, too.
And bandwidth. Our sources repeatedly highlight the massive bandwidth increases possible with light. How does that work here?
So this goes beyond just moving data quickly in sequence. It's about moving vast amounts of data simultaneously.
Okay.
The technique is called Wavelength-Division multiplexing, or WDM. Many listeners familiar with fiber optics will know this. WDM allows multiple data streams to travel down a single optical path, like a waveguide, on a chip, at the same time.
How?
By encoding each stream on a different wavelength, essentially, a different color of light.
Yeah.
They don't interfere, and you can separate them easily at the destination.
Oh.
This offers a dramatic increase in parallel data throughput compared to a single electrical wire.
So it's like upgrading from a single-lane road to a multi-lane superhighway, but using the spectrum of light.
Exactly, but doing it all within the confines of a computer chip or, system interconnects.
Yeah.
Then consider energy.
Right, the heat problem.
Photons traveling through optical media, like the waveguides used in photonic circuits, they encounter very little resistance.
Which means they lose very little energy along the way. Not much friction, so to speak.
Compared to electrons fighting their way through wires, the energy loss for photons is minimal. This directly translates to significantly lower heat generation and vastly reduced power consumption for performing the same computational work. It's a fundamental efficiency game, really critical for today's energy-hungry computing landscape.
And interference. We know electrons, being charged particles, can interfere with each other when you pack them close together. Crosstalk.
Exactly. Photons carry no charge. They are basically immune to the electromagnetic interference and crosstalk issues that plague increasingly dense electronic circuits.
So you can pack things tighter?
Potentially, yes. It allows for potentially much tighter packing of photonic components and more complex circuit designs without those signal integrity problems you get with electrons.
Okay, so speed, bandwidth, low energy loss, no interference. That's compelling. But how does light actually compute? The sources mention inherent parallelism. What's that about?
This is where light's unique wave properties really come into play. Optical systems can naturally perform certain operations simultaneously across an entire data set. The sources often use the compelling example of a simple lens.
Lens. Like in a camera, a telescope, your kit.
Yes, precisely. A simple glass lens can perform a mathematical operation called a Fourier transform on an entire image.
The whole image at once.
Instantly.
Yeah.
Processing every pixel simultaneously based on how the light waves interact as they pass through it. Electronically, performing that same complex operation requires breaking the image down, running enormous numbers of sequential or parallel calculations.
Wow.
Light can do it in a single instant optical process. It's a very different way of processing information.
That distinction is profound. It's not just doing the same thing faster, it's doing it differently, and in some cases like that, much more efficiently in parallel.
Exactly.
So these fundamental advantages, they translate into some concrete benefits for us, the people who actually need all this processing power.
They absolutely do.
Yeah.
These physics advantages aren't just, theoretical talking points. They directly address the limitations we talked about with electronic computing.
So we're talking about unprecedented processing speeds, leveraging that inherent speed of light for computations, and drastically reducing latency. Is that fair?
Absolutely. For tasks that demand real-time analysis, massive simulations, or handling enormous complex data sets, this offers the potential for performance levels previously unimaginable with electronics alone.
And that massive data throughput you mentioned from WDM.
It's critical for the age of AI and big data. Training large machine learning models, real-time analytics, processing streaming data from sensors, these all require moving and crunching huge volumes of information simultaneously.
And photonics is suited for that.
Uniquely suited for this, yes.
And the energy efficiency gains. Our sources hint at potentially tenfold or even greater power reductions for certain tasks. Is that realistic?
That figure, tenfold or greater, it comes up a lot in the research. It's staggering when you think about the energy footprint of global computing.
Yeah.
It represents a path towards a significantly more sustainable and, frankly, cost-effective computing infrastructure.
And ultimately, it offers a way to continue pushing the boundaries of performance scaling without being solely reliant on shrinking transistors further and further.
Into the quantum realm, yeah.
Where things get weird and expensive.
It bypasses those physical limits by shifting the computational medium entirely, from electrons to photons.
So, where is this photonic power most likely to shine first? What applications are really positioned for the biggest impact, do you think?
Well, many fields stand to be fundamentally reshaped. Artificial intelligence and machine learning is probably the most talked about right now.
Right, because AI workloads, especially things like deep learning, they rely heavily on matrix multiplications and linear algebra, don't they?
Correct. And it turns out photonic processors are exceptionally efficient at performing these specific types of linear operations very quickly and very energy efficiently.
Okay.
Companies are already demonstrating photonic AI accelerators that show really compelling performance advantages over traditional electronic GPUs for these particular tasks.
Outperforming GPUs already for specific AI jobs. That's where this gets really interesting. It's not just a future idea, then.
It's impacting current benchmarks, yes. It's happening now. Data centers are another clear application area.
Makes sense. They already use fiber optics extensively for communication between racks and servers.
Moving data quickly across the floor using light instead of miles of copper wire. Yeah.
So what's next there?
Building on that, The trend is towards integrating optics much closer to the processing chips themselves, something called co-packaged optics,
Why?
to overcome bandwidth and power bottlenecks within the server itself, getting data on and off the chip faster and more efficiently.
Ah,
The long-term vision includes all optical switching and even processing inside the data center to maximize efficiency and throughput. Less conversion between light and electricity.
high-performance computing, the supercomputers doing cutting-edge research, I assume they desperately need what photonics offers.
Absolutely. Achieving exascale computing and beyond, enabling complex simulations in climate science, materials research, financial modeling. These efforts are often limited by the power and data movement bottlenecks in current electronic systems.
Photons can help.
Photonics offers the necessary speed and bandwidth to push those frontiers, reduce those bottlenecks.
And telecommunications. Fiber optics is the backbone of modern networks. Does this build on that?
It does. Photonic computing can potentially process network signals directly in the optical domain, meaning eliminating the need for repeated and energy-intensive optical to electrical to optical, or OEO, conversions every time a signal hits a switch or router.
Which happens a lot.
A lot. This speeds up the network and reduces its energy footprint significantly.
What about quantum computing? Is there a connection there? The sources mentioned it.
There's a significant synergy, actually. While it's a different type of computing, photonics is crucial in several quantum approaches.
How so?
Well, photons themselves can serve as qubits, the basic units of quantum information in certain designs.
Okay.
And additionally, even for other qubit types like trapped ions or neutral atoms, photonic components are essential for controlling and reading out their states.
Like lasers and detectors.
Exactly. And also for connecting future quantum computers into networks. Photonics is key infrastructure there, too.
Fascinating overlap. And beyond the big computing categories, any other areas?
Sensing and imaging applications benefit greatly. Think about advanced systems like LiDAR for autonomous navigation.
Right, for self-driving cars.
Or high-resolution medical imaging. These often rely on sophisticated manipulation and processing of light signals already.
And integrated photonics helps.
Integrated photonic circuits allow these systems to become more compact, more efficient, and more powerful, putting more optical capability onto a small chip.
Okay, that list of applications is broad and potentially transformative. It sounds almost inevitable then. Is it just a matter of time?
Well, while the potential is undeniable, our sources also make it very clear that significant challenges remain before photonic computing achieves, widespread adoption comparable to electronics.
Right, the reality check. Let's unpack those hurdles. What's slowing things down?
Okay, one major challenge is miniaturization and achieving density on par with electronic chips.
Making things small enough.
Yeah. The wavelength of light itself, while tiny, is typically larger than the smallest features we can now reliably etch onto silicon using current manufacturing.
So light is bigger than the smallest transistors.
In a sense, yes. Making photonic components as small and packing them as densely as billions of transistors is just physically difficult.
So the very nature of light imposes a kind of scaling challenge.
It does. Another hurdle is seamlessly integrating photonic components with established CMOS electronic technology. Because for the foreseeable future, we'll likely see hybrid systems, right? Light and electrons working together.
Makes sense.
Making that interface between light and electrons efficient and reliable on a single chip is a complex engineering problem, getting the signals back and forth without loss.
And the materials. What do you build these things out of?
That's a big one. Developing and manufacturing materials with the precise, stable optical properties required for computation.
Light.
Things that don't change with temperature, that guide light perfectly. And doing so at scale with high manufacturing yields, that's still an active area of research.
But there's progress.
Oh yes, silicon photonics, which leverages existing silicon semiconductor manufacturing infrastructure, is showing great promise here, using the tools we already have.
Leveraging existing fabs sounds like a smart path forward. Cuts down costs and development time.
It's key for manufacturability and cost reduction, definitely. There's also the challenge of precisely controlling light on the chip at the micro and nano scale.
What does that involve?
Generating light efficiently on the chip, ideally tiny lasers, modulating its properties like turning it on/off or changing its intensity very fast, routing it along specific paths without it leaking, and detecting it accurately at the other end. All of this requires incredibly sophisticated design and fabrication. It's not trivial.
And earlier you mentioned the idea of analog noise. That sounds tricky.
Right. Many current photonic approaches are analog. They encode information in the intensity or phase of light, which, unlike digital's clear zeros and ones, can be susceptible to noise or fluctuations.
So calculations might not be perfectly precise?
It can limit the precision compared to digital electronic systems. Developing robust designs and potentially optical error correction techniques is pretty vital here.
And finally, the software and design tools. You can't build it if you can't design it easily.
Exactly. Just like electronics needed decades to build a mature software and design tool ecosystem, photonic computing needs the same.
So engineers need standard tools.
Engineers and programmers need standardized tools, simulation software, and design kits, like libraries of pre-designed components, to easily design and program photonic hardware. That infrastructure is still very much under development.
Okay, those are indeed significant challenges, but the sources also highlight that immense progress is being made, aren't they? It's not stalled.
Absolutely not. This isn't just a futuristic concept stuck in labs. Real-world technical barriers are being overcome at a really rapid pace.
Like the development of advanced photonic integrated circuits, or PICs, which are sort of the optical equivalent of electronic ICs, right?
Yes, creating complex light-manipulating circuits on a chip. Researchers are also making strides in novel materials, exploring things like phase change materials, the stuff used in rewritable DVDs, potentially for creating optical memory or switches that can operate entirely with light holding a state.
Interesting. And improved manufacturing processes, especially leveraging those existing semiconductor foundries for silicon photonics.
That's crucial for moving beyond lab prototypes to scalable production, making it manufacturable and affordable.
Yeah.
We're also seeing breakthroughs in key component design, more efficient light modulators, highly sensitive detectors, and real progress towards getting efficient light sources, tiny lasers, directly onto the chips themselves, which has been a long-standing challenge.
And the algorithms and architectures are evolving too, I assume. You can't just run standard software on this stuff.
Definitely not. Developing the right algorithms and designing computational architectures that are specifically tailored to leverage the strengths of photonic hardware, that inherent parallelism, the speed is a huge area of progress. Thinking differently about how to compute.
And our sources pointed to some tangible proof, didn't they? Mentioning demonstrations from companies like Lightmatter and Lightelligent.
They did. These companies and others too have demonstrated integrated photonic processors performing complex AI computations.
Real-world tasks.
Yes, real-world AI tasks, and showing clear speed and energy efficiency advantages compared to state-of-the-art electronic hardware like GPUs on those specific workloads.
So it's not just theoretical anymore.
These aren't just theoretical demos. They show real-world technical hurdles are being cleared. It works.
So while challenges remain, the trajectory is becoming clearer. It feels like there's real momentum.
It is. It's moving from lab possibility to a viable technology with a clear path towards practical implementation in certain areas.
Okay, so to bring this deep dive to a close, it seems clear that electronic computers aren't disappearing anytime soon. They'll remain essential for countless applications.
Oh, absolutely. But photonic computing represents a genuine paradigm shift. It offers a path to overcome those fundamental physical limitations currently facing electronics.
The heat, the power, the latency.
Exactly, particularly for the most demanding computational tasks in AI, data centers, and high-performance computing.
Its core advantages in speed, bandwidth, and especially energy efficiency make it uniquely positioned to redefine what's possible in an era increasingly dominated by massive data.
And based on the pace of recent breakthroughs and these demonstrated capabilities we talked about, it's transitioning rapidly from a theoretical concept to a technology that is very much on track, I think, to become a cornerstone of our future computing infrastructure.
So the age of computing with light is perhaps closer than many people realize.
It feels that way, yes.
So here's something to think about. Considering the sheer scale of change, this promises potentially overcoming fundamental physical limits, drastically improving efficiency. How might computing with light truly reshape the industries that rely on processing massive data at speed? And maybe which potential application excites you the most?
That's a great question to ponder. The future looks, well, luminous.